Hello, my name's Darren Holmes, and today in AC Electrical Circuits, we're going to be taking a look at lab number 1, basic RL and RC DC circuits. We're going to perform the entire lab using National Instruments Multisim to simulate these circuits. The objective of this exercise is to become familiar with the basic behavior of capacitors and inductors. This includes determination of the equivalent, series, and parallel combinations, the division of voltage among capacitors in series, the DC steady-state behavior of simple RLC circuits, and the transient behavior of RC circuits will also be examined. I will be using Sham's Outlines, Basic Electricity, 2nd edition. I'd like to recommend to students who are not purchasing the textbook that you get a copy of Sham's Outline, Basic Electricity, 2nd edition. This book is a good choice for students who aren't purchasing the textbook because it's only $22. It's available through your bookstore or online. You can also buy it at the Google Play Store as a $15 PDF download. So under reference sections, we're going to be looking at Chapter 13 on inductance. Just the first 7 pages. We're not into reactance yet. We're going to look at Chapter 14 on capacitance, the first 5 pages. And Chapter 22 gives us a little review of waveforms and time constants. Chapter 13 is all about inductance. It talks about characteristics of coils, and it has a section on inductors in series or parallel. So in series, coils add together, and in parallel, they add similar to resistors. Chapter 14 is all about capacitors. They talk about charging and discharging capacitors. They talk about the types of capacitors. They talk about capacitors in series and in parallel. And when you put capacitors in series, they add similar to resistors in parallel. And when you add capacitors in parallel, they simply add together like resistors in series. Chapter 22 talks about waveforms and time constants. And figure 22-2 shows you the response of circuits with R and L in series. So you can see that there is a certain charge curve and a certain discharge curve. Figure 22-2 continued shows you the voltage waveforms of VR and VL. Figure 22-4 shows you the rising exponential current. And there's a section on RL time constants. There's a section on RC series circuit waveforms. And figure 22-6 shows you the response of a circuit with R and C in series. Under theory overview, it says the inductor behaves identically to the resistor in terms of series and parallel combinations. That is, the equivalent of a series connection of inductance is simply the sum of the values. For a parallel connection of inductors, either the product, sum rule, or the reciprocal of the sum of the reciprocals rules may be used. Capacitors, in contrast, behave in the opposite manner. The equivalent of a parallel grouping of capacitors is simply the sum of the capacitances, while a series connection must be treated with the product, sum, or reciprocal rules. For circuit analysis, in the steady-state case, inductors may be treated as shorts, or for more accuracy, as a small resistance known as the coil resistance, and we call this R coil. With capacitors, may be treated as opens. So remember, a capacitor is just 2 plates separated by air or some kind of electrolyte. So with capacitors, we treat them as open circuits in a DC circuit. If multiple capacitors are in series, the applied voltage will be split among them inversely to the capacitance. That is, the largest capacitor will drop the smallest voltage. It says the steady state is reached after 5 time constants, usually denoted by the Greek letter tau. So the time constant for an RC circuit is simply the effective capacitance times the effective resistance. So tau is equal to RC. So what we're saying is if you multiply R by C and then multiply by 5, that's how long it will take the capacitor to charge up. In the inductive case, the time constant is the effective inductance divided by the effective resistance. So tau equals L divided by R. I just want to remind everybody from our first semester, the percent error calculation has not changed. We're going to take the absolute value, so these two lines here mean the absolute value of the theoretical value minus the experimental value. So if the experimental value is larger than the theoretical value, we're going to get a negative number, but we're going to take the absolute value of that, so it's always a positive number. So we just take that positive number, divide it by the theoretical value, multiply it by 100 to get our percent error. Keep in mind the theoretical value is the actual known nominal or labeled value. So under equipment, we're going to be using a DC power supply. Now in our case, it's going to be a multisim component. We're going to use a digital multimeter. This will be a simulated multimeter that we're going to use in Multisim. And when we do this lab in the physical lab room, I tell everybody just to use the computer and go out to Google and find a stopwatch. But I want to show you something on, this is Windows 10 I'm using. So if you just type in, I think it's alarm. Okay, we have something called Alarms and Clock. It's an app. So if you click on that, right, we have an alarm clock. We have a regular world clock. Oh, look, I'm right here in Canada. We have a countdown timer. And finally, we have a stopwatch. So when you click on the play button, you can see it counts up. So that would be seconds. That would be hundredths of a second. We can pause it and reset it. Next, these are the components that we're going to be using. So this is the required parts list for AC electrical circuits. And under my name, I was assigned these measured values. So you can see my 1 microfarad. This is my polarized or electrolytic capacitor. I need to use 1.061 microfarads. So this is what I have to simulate in Multisim. It's also the number I have to use to do all my calculations with. Your numbers will be assigned to you, and they will be different from my set of numbers. So under procedure, step number 1, we're supposed to use a DMM to measure our component values. Now because we're simulating this circuit, you've all been assigned component values. So I'm going to show you how to edit the lab and get it ready to hand in, and we'll enter our assigned values into the lab. Now because we're going to be simulating this lab, you're going to need to get a copy of National Instruments Multisim. On my YouTube channel, I have a how to find and install Multisim, and it comes with a 30-day free trial. Once that free trial expires, you'll need to get a license, and typically you'd get it through Utica. It's about $60 Canadian. The next item you're going to need is some kind of word processor. If you have Microsoft Office on your laptop, that's great. You can use that. I have a few how-to videos on how to use Microsoft Office. If you don't have Microsoft Office, I have a video on my YouTube channel on how to get LibreOffice, which is a completely free open source word processor and Excel spreadsheet. So I'm just going to go ahead and open LibreOffice. And typically I'd go to Open File and I would go to my Downloads directory, and you can see I have 2018 AC Circuits Lab 1. It's a docx file, which is a Microsoft Word document. So I'm just going to click on that and say Open. And you can see that opens it up into a program called LibreOffice Writer. Now, because you have to hand in the lab electronically, we might as well use the existing Word document and just modify it for hand in. So the first thing I'm going to do is go down here and just zoom in a little bit. The top portion is called a header. So every page has a header and a footer. So just go ahead and double click in that area, and you can see it says header, first page. So here where it says student name, just highlight that underscoring and put your name in. And then where it says student number, just put your student number in there. And then just click somewhere else in the document. And now you're out of the header. Now you can see I've got a little problem here with the title, so we'll just fix that up. When you're handing this in, you don't need to hand in stuff like objective, so just highlight it and hit delete. We don't need the references. Delete that. All the theory overview. Error calculation. I'm going to leave in the equipment. So we don't need this extra space up here. Okay, then for the stopwatch, we don't need to keep that. So under components, everybody got their component list. So you should be using your components. So put those values in there. So under schematics, we don't need these individual schematics because we're going to put in a screen capture of our schematic. So I'm just going to delete those. Procedure, we don't need the procedure, so I'm just going to highlight the procedure. And we're going to need the data tables, so procedure's gone. So there's our data tables. We're going to need those. Now down here we have plots. Now when it comes time to do the plots, I'm going to show you how to do those in the spreadsheet program. And then we've got questions down here. The thing about the questions is when you highlight it, notice how it drops down. I didn't leave you space to type anything in. So what we're going to do is we're just going to highlight all of these. So once you've highlighted all the questions, we're going to go to Format, and under Format there's a paragraph option, so click on that. And in spacing, we want the spacing to be 0 centimeters above and 0 centimeters below. So we're not going to add spacing between paragraphs. The line spacing is going to be single. So click on OK, and you can see it puts all the lines in here for us. Now keep in mind this are in kind of a bullet form. So whenever you press enter over here, it's going to put in another number. Okay, so I'm going to show you how to get rid of those later. But for now, we just got rid of all the blank spacing. So this plot is a graphic, so hit delete, get rid of it. And this plot's a graphic, so just hit delete and get rid of it. Okay, so now our lab is in a format that's ready to hand in. We're not going to know about all the spacing and everything until afterwards, so we'll worry about it later. So I'm going to save this file. So we go to File, Save As, and we want to change the name of it, right? So whatever your course code is, so that should be the first thing that you type in here. So I think it's something like ELT. It's probably a second semester course, so ELT 201 space. Then we want to tell it what kind of lab it is, so it's AC and it's lab 1. Next thing we want in here would probably be your student number. We want you to follow that with your last name and then your first name. Okay, so when you submit this to your teacher, he knows what course it is, what lab it is, and the student number is sometimes very important because we have a lot of people with the same last name. So it really helps your professor when you do something like that and put your student number in there. So what we're going to do is save. And please continue to use the Word 2007 to 365 format. Okay, so if your professor's using Word at home, he's probably got a college laptop and has Office already installed on it. So it really helps if you keep it in the Word format for him. Okay? So when you're typing in resistance, we'd like to see the little ohm symbol. So you'll notice up here we do have some symbols. So we should be able to find the little ohm symbol somewhere. And there it goes. So once you've finished typing in all your component values, you might as well clean up the page by getting rid of the extra information that we don't need. Then underneath schematics, we're going to put a screen capture of our circuit from Multisim. So for right now, we'd like the data tables to start on a new page. So if you just click the space between schematics and data tables, press down the Control key and press Enter. It will now put data tables on the next page. You can see we have an extra blank line in there, so you can get rid of that. So now we're ready to set up and start doing the lab. So now we're going to switch to Multisim and start working. So under Procedure 1, it says using these values determine and record the theoretical series and parallel combinations specified in Table 1.1. So everybody's got different values, so I'm going to use the nominal values. So that is, if I was supposed to use a 1 microfarad capacitor, I'm going to do the calculations based on 1 microfarad. You're to use your assigned measured values for these calculations. So on table 1.1, we can see the first pairing is the 1 microfarad in series with the 2.2 microfarad capacitor. To do the calculation, we take the 1 microfarad times the 2.2 microfarad divided by the 1 microfarad plus the 2.2 microfarad. In this case, it works out to 687.5 nanofarads. In the second pairing, we have 1 microfarad in parallel with 2.2 microfarads, in which case we just add the two together and we end up with 3.2 microfarads. So under Procedure, step number 2, we're to connect the two capacitors in series and measure the total capacitance using the DMM. We're to record this value in Table 1.1 under the experimental column. We're to repeat this process for the remaining combinations in Table 1.1, also determine and record the deviations. So we're going to start up National Instruments Multisim 14.1, double left clicking on it. I am using the Multisim Student Edition, the same one you would be using at home. So to start off with, we're going to go to Place, and we're going to place a component. We're going to narrow down the groups. We're going to select Basic, and under Basic we want Rated Virtual Components, and we're going to be using the polarized rated capacitor. So just click on OK and just drop that somewhere on the page. Now we're to put two capacitors in series. So there's my second capacitor. I'm just going to press close. Now to wire two capacitors in series, we go to the end of the first capacitor, and you notice the pointer turns into crosshairs, so just do a left mouse click and then drag your wire over to the second capacitor and then do a second left mouse click. So now our two capacitors are connected in series. Now our first capacitor came up as 1 microfarad, and we're supposed to be using our assigned measured values. So if you double left click on C1, you can see the capacitance can be changed. So my capacitor was 1.061, and that was in microfarads. So I'm going to click on OK. Now my second capacitor, the 2.2 microfarad capacitor, actually came in at 2.567 microfarads. So I'm going to click on OK. So these are my two capacitors in series. Now I'm supposed to measure the total capacitance of the two capacitors in series. So if you come over to the right hand side of your screen, these are your equipment that you have access to. So I have an Agilent multimeter. So I'm going to click on that and bring it over. Now obviously one lead is going to go to this side of the capacitor. The other lead will go to this side of the capacitor. So let's take a look at our Agilent multimeter by double clicking on it. And when we look at the functions available on this multimeter, you can see I have DC volts, AC volts, ohms, frequency, and continuity. Nowhere on here do I have any way to measure capacitance. So I cannot use this meter to measure my total capacitance. So this Agilent multimeter is of no use to me, so I'm just going to click on it and press delete to get rid of it. So now I'm going to go back to the right hand side of the screen, and the first item is a multimeter. So I'm going to click on that, drag it over. So you can see the positive. I can drag a lead down and over, and when I try and go down, the whole lead drags down with it. So if I just do a left mouse click, that will anchor it so that I can go down and over and make that connection. Then the negative, I can go down, over, and once again I need to anchor it, so do a left mouse click, drag it down and over. So this is how we would connect a capacitance meter. Now when I double click on it, I can measure current, volts, ohms, and dB in AC and DC. So once again, in Multisim, I do not seem to have a meter that can measure capacitance. So I'm going to have to go out and show you how I would have done this using benchtop equipment. So you can see I have two capacitors, and the first capacitor here is 2.2 microfarads, and the second one is 1 microfarad, and I have them joined together in this bus here. So my digital multimeter comes in on the red line, goes to the longer lead. It comes out the shorter lead, goes to the longer lead of the second capacitor, comes out the shorter lead of the second capacitor, and goes back to common of the digital multimeter. So up here on your digital multimeter, the red lead goes into the hole labeled volts, ohms, capacitance, and hertz. And you can see they're using the capacitor schematic symbol. The black lead goes into common. The large selector knob needs to be rotated clockwise until it comes round to the capacitor symbol. And you can see my reading is 749 nanofarads. I've now connected my two capacitors in parallel, and the DMM is reading 3.626 microfarads. So when it comes time to filling in the data for table 1.1, you can see my value for 1 microfarad in series with the 2.2 microfarad is 687.5 nanofarads. Yours will be different. The experimental series equivalent, not applicable because I cannot simulate it in Multisim. Same with the percent deviation. When it came to the 1 microfarad in parallel with the 2.2 microfarad, I calculated 3.2 microfarad. Remember, yours is going to be different. Experimental. Once again, I could not do this in Multisim because Multisim does not have a capacitance meter. So under step 3 of the procedure, we're to consider the circuit of figure 1.1 using an applied voltage of 5 volts. C1 will be our 1 microfarad capacitor and C2 will be our 2.2 microfarad capacitor. We're to determine the voltage across each capacitor and record these voltages in table 1.2 under theory. So you can see figure 1.1 is an applied voltage connected to two capacitors in series. So C1 will be our first capacitor, C2 is our second capacitor. So in table 1.2, checking my textbook for the formula, V1 is equal to 1 over C1 divided by 1 over C1 plus 1 over C2 times the applied voltage. So the voltage across capacitor number 1 is going to be 1 over C1 divided by 1 over C1 plus 1 over C2 times 5 volts, and that works out to 3.4 volts. The voltage across capacitor 2 is 1 over C2 divided by 1 over C1 plus 1 over C2 times 5, and that works out to approximately 1.6 volts. So on table 1.2, you can see I've recorded under theory for voltage across capacitor C1, I'll have 3.4 volts, and for the voltage drop across capacitor 2, I'll have 1.6 volts. So under procedure, step number 4, we're to build the circuit of figure 1.1. And remember, we're going to be using our assigned values for C1 and C2. We're to measure the voltage across each capacitor and record these values in table 1.2. And we're also to determine and record the deviations. So you can see I have my two capacitors still in my Multisim design. My C1 was 1.061 microfarads and C2 was 2.567 microfarads. Your values will be different. So the next thing I need to do is place a power supply. So I'm going to go to Place Component, and under Group, this is going to be Sources. I need a power source. It's going to be a DC power source, and you can see the schematic symbol is for a multi-cell battery. So I'm going to click on OK and drop my power source in. I'm also going to need a ground. So I'm going to throw my ground symbol in. Now I'm going to close my Place dialog box. So I need to connect the positive of my source to my capacitor. the negative end of the source goes to ground, and the output of my two capacitors need to connect back to the ground. And I like to leave a little space, so I'm going to press the left mouse button to anchor it, and then drag my wire back to the ground. So this is my completed circuit. Now remember, our voltage is supposed to be 5 volts, so just double click on the voltage. It comes up as 12. I'm going to put in 5 and say OK. So the next thing that I want to do is put a couple of multimeters to measure the voltage across C1 and the voltage across C2. So I'd like to leave some space at the top here for my meters. So what I'm going to do is I'm going to drag a box around my circuit. And you notice it's highlighted all the parts of my circuit. So now if I just hold down the left mouse button on any part, I can now drag my circuit to anywhere I would like it. So I'm just going to move it down out of the way and just click anywhere else on your design, and it will stop highlighting all the components. So what I'm going to do is come over to the right hand side, and I'm looking for a multimeter. So I've got an Agilent multimeter, so I can bring that over, and that's going to measure the voltage drop across C1. Now in the lab room we'd only have 1 meter, but since we're doing simulations, we actually have access to multiple multimeters, so we might as well make use of them and bring them in one at a time. So now I have 2 meters in my circuit. So now I need to know which of these connectors here have to be connected across my capacitor. So double clicking on my multimeter and just dragging it out the way a little bit here. Looking at these terminals, I can see volts and ohms is this red terminal here, and this seems to be the common for it. So looking down here, we can see the first hole comes out as the first line, and the common is actually the third, so we need the first and third connected across our capacitor. So make sure the component is not active, so you can see there's no blue box around it. So the first output needs to come down, over, anchor, and down to this side of my capacitor. Then the third connector down goes to the other side of my capacitor. So now I can measure the voltage drop across C1. Now I need to do the same thing for the second voltmeter. So I can bring the wire down and over. I can either bring it to the capacitor, or I can just bring it straight across to the other wire going to the common of my multimeter. Either way, it's going to be looking at the voltage at the top of C2. Now the third connector down has to go to the bottom of C2. So now I'm looking at the voltage across C2 with my second meter. So you notice the first meter is labeled XMM1, and my first meter here is labeled XMM1. If I double click on my second meter and move it out of the way, you can see it's labeled XMM2. So those are my 2 meters. Now obviously to see anything on the meter, we have to turn the meters on. So turn on both meters. They come up as AC voltmeters. We need them to be DC voltmeters. You'll notice on the meter we have the connecting terminals that now have a little white symbol with a cross on them, indicating those are the 2 terminals I have connected across my capacitor. Same thing with my second meter. Now I'm not getting any readings, so I do need to start my simulation. So that's the green triangle. Just click on that or press F5. Now down in the bottom right hand corner we can see the time. So we're actually now at 3 seconds, 4 seconds in. So this little symbol down here with the green bars going back and forth tell us that our simulation is running. And by now we should have voltage drops across both of our capacitors, and I'm not sure why it's not happening. So what we're going to do is turn off the meters and stop the simulation. And I'm just going to get rid of these 2 meters on here. So we need to modify our circuit a little bit here. So I'm just going to highlight the power supply and the ground. And I'm just going to slide them over a little bit just to make some room here. Then on this wire here, just click on it and press delete so that the wire is gone. Then I'm going to go up to place, component, and underneath basic I want to place a switch, and we can just use dip switch 1. It's perfectly okay. And I want to throw it into my circuit here. So I'll close that box down. Now I'm going to wire the switch into my circuit. So whenever you press the A key, the switch will either open or close, or you can use the little hand and just click on it, or use the A key to open and close your switch. So right now the switch is open. I'm going to open up my 2 multimeters. I'll just move them out of the way a little bit so that you can see the switch. I'm going to turn on the first voltmeter and the second voltmeter. So the first one is the voltage across C1, the second one is the voltage across C2. So I'm going to start my simulation, and this time you can see the voltage drop across both capacitors are 0. So I have no current going into my circuit. So now I'm going to press the A key, and now voltage is applied to my circuit, and you can see the capacitors charge up. So the voltage drop across C1 is 3.53776 volts DC, and the voltage drop across C2 is 1.462234 volts DC. So going back to table 1.2, under experimental for voltage across C1, I've recorded my 3.5 volts, and for the voltage across C2, I've recorded my 1.46 volts. I'm going to leave you to calculate the percent deviation between experimental and theory. Please keep in mind, my theory uses the nominal values. You're to use your measured assigned values to do those calculations. So moving on to the RL circuit, under procedure, step number 5, we're going to be using figure 1.2. Our applied voltage is 10 volts. We're going to be using the 47 k ohm resistor and the 10 millihenry inductor. I just want to remind you that you're to do all your calculations and measurements using your assigned measured values. So using your assigned measured values, we're to calculate the time constant and record it in table 1.3. We're also to calculate and record the expected steady state inductor voltage in table 1.3. So this is figure 1.2. We're going to be using 10 volts, a 47 k ohm resistor, and a 10 millihenry inductor. So in table 1.3, tau is equal to L divided by R, which is 10 millihenries divided by 47K, and that worked out to 212 nanoseconds. So that's going to charge up really quick. VL theory is just voltage divider. Now ideally an inductor is 0 ohms, but ours turned out to be 22 ohms, so using the voltage divider law of 22 ohms divided by 47K plus 22 ohms times 10 volts,
works out to approximately 4.7 millivolts. So we should see a very, very small voltage drop across the inductor.
So under procedure, step number 6, we're to set the power supply to 10 volts, but do not hook it up to the remainder of the circuit. After connecting the resistor and inductor, connect the DMM across the inductor, set to read DC voltage on the 20 volt scale. So I'm going to start building the circuit on a fresh design. So I'm going to go to Place, Component, and the first thing I'm going to do is place my source. So power source is going to be a DC power source, so I'll place that. I know I'm going to need a ground reference, so I'm going to place that. Under groups, I'm going to go to Basic and Rated Virtual. So I know I need a resistor. So I'll get resistor rated, and I'll throw that in my circuit. And I need an inductor, so inductor rated, and I'll throw that in my circuit. So I need to rotate my inductor 90 degrees, so I'm just going to left click on it, do it right click, and rotate 90 degrees clockwise. So now I'm just going to hook my circuit up as I normally would. So there's my circuit hooked up. Now keep in mind the voltage source is supposed to be 10 volts, so double click on that and change it to 10. Say OK. Now my resistor's the 47 k ohm resistor, and we're to use our measured component values. So my 47 k ohm resistor was assigned to me as 46.7 k ohms. So I'm going to say OK. And we're supposed to use a 10 millihenry inductor. And looking at my components, the inductance for my 10 millihenry inductor is actually 10.145. Now in here we have a coil resistance, and the coil resistance for my 10 millihenry inductor is actually 22.2 ohms. We don't need to change any of the other settings, so I'm going to click on OK. So this is my circuit set up. Now I need a multimeter, so I'm going to come over to the right hand side and see if I can find that Agilent multimeter and bring it in. Now remember, the first connector will go to the top of my inductor, and the third one is the reference point, so I need to bring that down to the bottom of my inductor. So I'm going to double click on my multimeter, and first thing I have to do is turn on the power and make it a DC voltmeter.
These are the three inductors that should have come in your kit. The one labeled 102 is 1000 or 1000 microhenries or 1 millihenry. The 222 is 2200 microhenries or 2.2 millihenries. And the 103 is 10,000 microhenries or 10 millihenries. I just wanted to show you your inductor. I have cut the plastic insulation from the outside off of the inductor, And when you take a close look at it, you can see it's just very fine wire. So over here I have two coils, and these are inductors, and you can see the legs are a little shinier. Basically, all an inductor is a coil of wire with a lacquer coating. A lacquer is just a clear paint, and that's all the insulation that is on these wires. I just wanted to show you that these thin wires are connected to the legs of your inductor. So they're very thin wires. They're just wrapped around the leg and then soldered in place. So if you spread the legs of these inductors too much, you will break these tiny wires, and they'll no longer be inductors. They'll actually be open circuits. You can also make an inductor by taking your standard hookup wire and wrapping it around something like a bolt or a nail, and this will create an inductor. I just wanted to show you that when you hook up a battery to an inductor, it becomes an electromagnet, and it can pick up things that are metal. If you de-energize the coil, it becomes demagnetized and it'll drop your metal items.
Under procedure, step number 7, we're to connect the power supply to the circuit. It says the circuit should reach steady state very quickly in much less than 1 second. We're to record the experimental inductor voltage in table 1.3. We're also to compute and record the percent deviation between experimental and theory in table 1.3. So now I'm going to start my simulation. And you can see my simulated voltage drop across my inductor is 4.75148 millivolts. So going back to table 1.3, you can see my time constant calculated out at 212 nanoseconds. VL theory, now this was using the 47K and the 10 millihenry inductor, came out to 4.7 millivolts. VL experimental through Multisim is actually 4.75148 millivolts. So now I can leave you to calculate the percent deviation. So moving on to the RC circuit, under procedure, step number 8, we're to start using figure 1.3 with an applied voltage of 10 volts. And R1 is to be your measured 47K ohm resistor. R2 is your measured 1K ohm resistor. And the capacitor is your measured 1 microfarad electrolytic capacitor. So using your measured values, we're to calculate the time constant and the expected steady state capacitor voltage, and we're to record these in table 1.4.
So you can see on figure 1.3, I've labeled E as 10 volts, R1 is 47K, R2 is 1K, and C is equal to 1 microfarads. The 1K ohm resistor is in parallel with the source, so when we hook up this circuit, current's going to flow through the 47K onto the 1 microfarad capacitor, and then it's going to act like an open, so we should see 10 volts on this side of the capacitor. So in table 1.4, tau is calculated as R times C, which is 47K times 1 microfarad, and that works out to 47 milliseconds. And VC in theory should be 10 volts.
So sometimes when we're entering numbers into our table, you can see they don't actually center the way we would like them to be, and sometimes they're in an odd color. All you have to do if that happens is just highlight those cells and come up here, and you can see we have a line center. So now that centers them horizontally, but we want to center it vertically as well. So if we come up here to Format, and we come down to Align, and in Align we can go to Center. So now you can see it centered both horizontally and vertically. Now I don't know why the color's kind of a blue color here, so I'm going to come over here to my font color. I'm just going to click on black. And for some reason italic is on, so I'm going to turn that off. So it's fairly easy to fix anything in your tables here that doesn't look quite right. So little practice, you'll be able to do this as well. So under procedure, step number 9, we're to set the power supply to 10 volts. And it says after connecting the resistor and capacitor, connect the DMM across the capacitor set to read DC voltage. So this is my schematic setup here. You can see my applied voltage is 10 volts. It's a DC voltage. Now R2 is the measured value of my 1K ohm resistor. So mine was 995 ohms. That was assigned to me. My R1, that's the 47K ohm resistor. Mine was assigned as 46.7K. And C1 is my 1 microfarad electrolytic, and mine was 1.061 microfarads. So moving on to procedure step number 10, we're going to connect the power supply to the circuit. It says the circuit should reach steady state quickly in under 1 second. We're to record the experimental capacitor voltage and compute the percent deviation between experimental and theory. We're to record these values in table 1.4. So the first thing I need to do is turn the power on to my multimeter. Make sure that it is DC. So make sure it does say volts DC. You can see my input and my common are both connected together, so just double checking there. So I'm going to turn the simulation on, and you can see in about 1 second the voltage drop across the capacitor is 9.9999 volts DC, which is kind of what we expect. So when the power comes on, current flows through our 47K ohm resistor onto our 1 microfarad capacitor, but once the charge is reached, the capacitor acts like an open circuit, so it doesn't discharge to ground. So over here on table 1.4, I've recorded VC experimental as 9.99999 volts, so the percent deviation should be very small. I'm going to leave you to calculate that using your measured values. So moving on to the RC circuit with the long time constant. Under procedure, step number 11, we're still continuing to use figure 1.3, but now we're going to be using the largest capacitor we have, which is 470 microfarads. We're to calculate the time constant and the expected steady-state capacitor voltage, and we're to record these values in table 1.5. So I'm going to show you how to do the calculations using the values stated here, but when it comes time for you to do your calculations, you're to use your assigned measured values.
So this is figure 1.3. You can see we're still using 10 volts. 47K and 1K, but now we're going to be inserting a 470 microfarad capacitor. When we're charging the capacitor, the current is going to charge through R1 onto the capacitor. So tau is going to be R times C, so that's going to be 47K times 470 microfarad. When we remove the power supply, the capacitor is going to discharge through the 47K and the 1K. So now tau becomes 48K times the 470 microfarad capacitor. So looking at table 1.5, you can see we have charging and discharging. So for tau charging, it's 47K times 470 microfarads, which is 22.1 seconds. And it should charge up to 10 volts. Discharging it's discharging through the 47K and the 1K. So it's 48K times 470 microfarads, which works out to 22.6 seconds. And it should discharge down to 0 volts. Remember, to fully charge or fully discharge, we say that takes approximately 5 tau. So to fully charge, it should take somewhere around 113 seconds. And 113 seconds to discharge.
So in table 1.5, you can see I've put in my calculated value for tau, charging and discharging, and what voltage they should fully charge or fully discharge to. So under procedure, step number 12, we're to set the power supply to standby, which means the off position, and we're to wait a moment for the capacitor to totally discharge. So we know that's going to take approximately a couple of minutes. We're going to remove the capacitor and replace it with 470 microfarad capacitor, and we're going to reconnect the DMM across the capacitor. So here's my circuit, and you can see I've replaced C1 with my measured value of 471 microfarads. Now remember, when you're replacing components in a simulation, you have to turn the simulation off first. So under procedure, step number 13, we're to energize the circuit and record the capacitor voltage every 10 seconds as shown in table 1.6. This is the charge phase. So looking at the tables, I have an RC circuit charging and an RC circuit discharging. You'll notice there's an extra box around here. So I can actually move my cursor around, and notice the cursor changes shapes. So when I've got this little down arrow cursor, if I click there, notice how it highlights the whole set of boxes. So now if I come over here to Properties, and that should be on the right hand side of your screen, if you scroll down the dialog box for Properties, you notice it has Miscellaneous, and there's the borders. So if you click on borders, you can turn off the borders. So now when you click somewhere on the screen, you'll notice all that outline has disappeared. So you can just close this properties box down. So looking at RC circuit charging, we can see we start at time 0 and go all the way up to 150 seconds. Okay, so here's my circuit ready to be simulated, and make sure it's on DC volts. And now I'm going to go ahead and start my simulation. And whoa, notice it jumped immediately to the 10 volt supply voltage. So once again we have a little simulation error here, so I'm going to stop my simulation. And on this line here that goes from the 10 volts to my circuit, I'm going to click on that and press delete. And then I'm going to go up to place, component, and I want to place a switch, dip switch 1, OK, and put that into my circuit, close. Now wire this up to my circuit. Okay, so there's my switch. So I'm going to start with my switch open, and notice it's the A key activates the switch. So I can run my simulation with F5. I can pause my simulation with F6. So I'm going to start my simulation and immediately pause it. So you can see with my simulation paused at approximately 0.1 second, the voltage drop across my capacitor is 0 volts DC. Now what I'm going to do is I'm going to close my switch so that it'll actually start charging. So then I'm going to press run, and then I'm going to pause it when my timer at the bottom here gets to 10 seconds. So you can see at 10 seconds I've paused my simulation and the voltage drop across my capacitor is 3.62377 volts. So now I'm going to start my simulation and pause it again at 20 seconds. So at 20 seconds, the voltage drop across my capacitor is 5.94334. So now I'm going to start my simulation again and pause it at 30 seconds. So at 30 seconds, the voltage is 7.42476. So I'm going to start my simulation again and pause it at 40 seconds. So at 40 seconds, the voltage across my capacitor is 8.36083 volts. So I'm going to start my simulation and pause it again at 50 seconds. So at 50 seconds, the voltage drop across my capacitor is 8.96 volts even. So I'm going to start my simulation again and pause it at 60 seconds. At 60 seconds, the voltage drop across the capacitor is 9.34051 volts. So I'm going to start my simulation again and stop it at 70 seconds. So at approximately 70 seconds, I'm reading 9.58085 volts. So I'm going to start my simulation again and pause it at 80 seconds. At 80 seconds, the voltage drop across my capacitor is 9.73431 volts. So I'm going to start my simulation again and this time pause it at 90 seconds. So at 90 seconds, the voltage drop across my capacitor is 9.83180 volts. So once again, I'm going to start my simulation and pause it at 100 seconds. So at 100 seconds, the voltage drop across my capacitor is 9.89320 volts. So once again, I'm going to start my simulation and pause it at 110 seconds. So at 110 seconds, I'm getting 9.93245 volts dropped across my capacitor. So I'm going to restart my simulation and pause it at 120 seconds. So at 120 seconds, I'm getting 9.95672 volts dropped across my capacitor. So I'm going to restart my simulation and pause it at 130 seconds. So at 130 seconds, I'm getting 9.972272 volts dropped across my capacitor. So I'm going to restart my simulation and pause it again at 140 seconds. So at 140 seconds, I'm getting 9.98271 volts dropped across my capacitor. So I'm going to restart my simulation and pause it again at 150 seconds. So at 150 seconds, I'm getting 9.98897 volts dropped across my capacitor. So I've now completed table 1.6. I'm just going to zoom out a little bit here. And I just want to remind you about table formatting. So if we actually highlight all the cells in our table, we can actually go over here and center them. And that has centered them horizontally. So to center vertically, we go to Format, we go to Align, we come down here and click on Center. Under Procedure, step number 14, we're to remove the power supply from the circuit. and record the capacitor voltage every 10 seconds as shown in table 1.7. Now this is going to be the discharge phase. So I'm at 150 seconds right now, and I want to start discharging my circuit. The problem is, if I stop the simulation, I'm going to lose the charge on my capacitor. So I really want to open up the switch, watch my circuit discharge, but to use the timer that's part of the Multisim simulation, what I'm going to do is actually let the timer run to 200 seconds. So I'm going to restart my simulation, and I'll pause it when it gets to 200 seconds. So at 200 seconds, that's going to be my time zero for the discharging cycle. So I'm going to record 9.99886 as my starting voltage. So on the table, I've recorded 9.9986 as my starting voltage. So now at 10-second intervals, I'm going to record the individual voltages. Now remember, I'm starting at 200 seconds, so my first pause will be at 210 seconds. So before I start my simulation up, I'm going to open my switch. So now my capacitor will be discharging through R1 and R2 back to the ground, or the negative terminal of my capacitor. So starting at 200 seconds, I'm going to start my simulation and pause it at 210 seconds. So at 10 seconds, the voltage drop across my capacitor is 6.41718 volts. So now I'm going to run the simulation for a further 10 seconds. So at 20 seconds, the voltage drop across my capacitor is 4.11734 volts. So I'm going to start my simulation and let it run for another 10 seconds. So at 30 seconds, the voltage drop across my capacitor is 2.638 volts. So I'm going to start my simulation and run it for another 10 seconds. So at 40 seconds, the voltage drop across my capacitor is 1.692532. So I'm going to start my simulation and run it for another 10 seconds. So at 50 seconds, the voltage drop across my capacitor is 1.084103 volts. So I'm going to start my simulation and let it run for another 10 seconds. So at 60 seconds, the voltage drop across my capacitor is 694.555 millivolts. So I'm going to start my simulation and let it run for another 10 seconds. So at 70 seconds, the voltage drop across my capacitor is 444.396 millivolts. So starting at 60 seconds, we now have to put in our units, which are millivolts. So at 60 seconds, 70 seconds, onward, we'll always have to put in our units because we've switched from volts to millivolts. So I'm going to start my simulation up and let it run for another 10 seconds. So at 80 seconds, the voltage drop across my capacitor is 284.508 millivolts. So I'm going to start my simulation and let it run for another 10 seconds. So at 90 seconds, I'm getting 182.5963 millivolts dropped across my capacitor. So I'm going to start my simulation and let it run for another 10 seconds. So at 100 seconds, I'm getting a voltage drop across the capacitor of 116.5727 millivolts. So I'm going to start my simulation and let it run for another 10 seconds. So at 110 seconds, I'm getting 74.5624 millivolts dropped across my capacitor. So I'm going to start my simulation and let it run for another 10 seconds. So at 120 seconds, I'm getting 47.9531 millivolts. So I'm going to start my simulation and let it run for another 10 seconds. So at 130 seconds, I'm getting 30.8301 millivolts dropped across the capacitor. So I'm going to run my simulation for another 10 seconds. So at 140 seconds, I'm getting 19.66228 millivolts dropped across my capacitor. So I'm going to start my simulation and let it run for another 10 seconds. So at 150 seconds, I'm left with 12.62201 millivolts dropped across my capacitor. So this completes filling in table 1.7. Now while you still have this simulation on your page, what I want you to do is to move your multimeter up to the side here. And what we're going to do is capture a picture of your circuit and your final reading, and we're going to paste it into our word processor. So there's several ways to do this. We can use the snipping tool, or you can press Shift and print screen, and that will capture your screen. So when you go into your word processing document, what we're going to do is we're going to go up to the position where it says schematics, and right there where it says schematics, we're going to do a right click and we're going to do a paste. So you can see it pastes in your entire screen. So we need to do some editing on this. So what I'm going to do is right click, and we're going to do some cropping. So you notice the handles around the picture change when we do cropping. So we're actually going to click on one of those handles and drag it down. So we're just going to drag it down to the top of the meter. So now we've cropped it to the top of the meter. Then at the bottom, we're going to hold down the left mouse button, drag the box up to the bottom of our meter. So now we have a smaller diagram in here. So we're going to do the same thing with the left-hand side. Just drag it over to the start of your schematic. And the right-hand side, we can drag it over to the start of the meter. So if we click somewhere on the screen, we lose our handles. So now if you click on your picture, and if you grab one of these boxes, so if you grab a side box, we'll actually spread it out and it'll look strange. And if you drag a bottom box, it'll also look strange. So you want to grab a corner and just drag it over, and that repositions both the horizontal and the vertical. So then you can click on it and actually move it around on your page until you find a nice spot for it. So you want to make this as large as possible, but you still want it to fit on your page. So now we've put our schematic in. So now our professor knows that we actually did this simulation, and that last number there should be the last number on table 1.7. So under procedure, step number 15, we're going to use the data from tables 1.6 and 1.7 to create two plots of capacitor voltage versus time and compare them to the theoretical plots found in the text. So it says you can use plot 1.1 and plot 1.2. So instead of doing them with pencil, I'm going to show you how to do them using a spreadsheet program. So just finishing off our lab, under equipment for the DC power supply, my model number was, it was just generic, right? So it was a Multisim part number. And my digital multimeter, I used the Agilent, and it was the 34401A. And as far as serial number goes, I just put in Multisim. Now, one of the things that I need to do here is put my graphs in. So you can see I've got my RC circuit charging and RC circuit discharging. And I want to grab those numbers and put them into a graph. Now, one of the problems I'm going to have is I've put these in as millivolts, and I really need them to be a number. So I have to go in and edit these. So this is actually 0.694 and no decimal point there, and get rid of that MV. So it has to be a real number. It can't have text in the box as well as a number. Okay. So the next thing is I'd like to format this. So if you just highlight it, you can go into Table, and under Table we can go to Number Format. And under Category, this is a number. But we want to use scientific notation. So we'd like to have maybe 3 or 4 decimal places after it. And look, we can actually select engineering notation. So I'm going to go ahead and click on OK. So now you can see my number comes up as 694 times 10 to the power of minus 3, which is millivolts. So I'm just going to go ahead and change the rest of my numbers over. So I just want to remind you, when we went from 116 millivolts to 74 millivolts, we now have to put in the 0.074. So we have to continue to do that for the rest of the numbers, all the way up to 150 seconds. So I'm just going to go ahead and highlight all the cells at once, go into Table, select Number Format, under Category, select Scientific, and we should maintain the same number of decimal points. So I'm just going to put in 4 decimal points, and I want it in engineering notation, and click on OK. So now it's converted all my numbers over. So you can see when I went from 116 millivolts to 74 millivolts, the numbers came out correctly. So now I have all the data on my tables ready to be put into a graph. So I'm just going to show you one more little feature here. We can actually zoom out. So I want to zoom out so I can see my entire set of numbers there. Okay, so now I can select all my numbers at once. And down here at the bottom, we can do a multiple page view. So if you click on multiple page view, you'll notice we can pick up our table for charging and discharging, as well as our page for the plots that we're going to do. So to generate the chart, what I'm going to do is grab all the contents of the table 1.6. So I've highlighted all the cells in table 1.6. Now I'm going to come over here to my Insert Chart. And now I have to select the chart type. So this is going to be a line chart, and it's got points and lines in it, and I want to smooth the lines out. So you can see here it's trying to put this little chart in my table right now. So the next thing I want to do is check the data range. So that's my table, my data series, my chart elements. Now under chart elements, my title is going to be RC charging. My x-axis is time, and I want everybody to know that it's in seconds. My y-axis is voltage, and it's in volts. Now we want the display to have a grid on it so that I can take readings off of it. So I want an x-axis and a y-axis grid. Now it says display legend. That's this information right here. I don't want it to display the legend. Okay, so I think I'm finished. So I'm going to click on Finish. And you can see it's tried to put the chart in the middle of my table, and I don't want it there. So what I'm going to do is I'm going to come up here till I see those multiple arrows there, and just hold down the left mouse button. I'm going to try and drag it to another position over here. It does not seem to be anchoring for me. And when I let go of the mouse button, there we go. So it has anchored it there for me. Notice here where it says voltage, it's kind of screwed up my table. So I'm just going to go in there and fix up my table a little bit. So there's my chart. I can actually highlight it. I can make it larger, smaller, whatever I need to do. So now I'd like to put the discharging chart in. So I'm just going to grab all the data on this table. And then I'm going to come up here to Insert Chart. And it's going to be a line chart, points and lines. And we're going to smooth out the lines. And under titles, it's going to be RC looks good. X-axis once again is time, and it's in seconds. And the y-axis is voltage, and it's in volts. Once again, we want both axes, and I'm going to turn the legend off. So I'm happy with that. I'm going to click on Finish. So once again, it's tried to stick it in the middle of a table for me, so I'm just going to grab the whole thing and drag it over here. And there we go. Once again, it screwed up my title here for voltage, so fix that. There we go. Yeah, I'm not sure what's going on over here, so I'm just going to drag the box down a little bit. There we go. Whoops, too far. So try and center these so the two graphs kind of line up underneath each other. So on the last page of the lab, we have 7 questions for you to answer. I showed you how to get rid of the formatting so that we didn't have a large spacing after each of these. The thing to keep in mind, though, is if you get to the end of a line and you press Enter, it gives you the next item. So we don't want to do that. So come up here and click on Undo. So when you get to the end of a line and you want to put another line in without it creating a new bullet item, what you do is you hold down the Shift key and press Enter. So now you can type your answer, and you'll notice that it actually indents it for you. So if you want to put a blank line after that, just press down Shift, Enter. There's your next blank line, and now you can continue on with your next question. At the bottom here, we have a space for instructor's initials. We're not going to bother with those because we're doing a simulation at home, so you can delete that line. And I've answered all my questions. So it's kind of important to save these documents when you're working on them. So since we've already given it the name that we want it to have, you can just go ahead and click on Save. And like I said before, we'll use the Word format. So So once you're happy with how your document looks to hand it in, what we're going to do is we're going to go to File, and we're going to go to Export. And then we want to choose the type that we want to export it to. We're going to export it as a PDF. So we can keep the same file name and export it as a PDF. Click on Save. And we're just going to keep everything as it is and click Export. So now I'm going to go to Microsoft Windows Explorer, and I'm going to go to my, I think I stored this in Downloads. So you can see my document that's the Word document, and this is the PDF version. So go ahead and double click on the PDF version, and mine brings it up in the Edge browser. So then just scroll through your PDF. Make sure that everything looks the way you thought it should look. So there's my RC charging. There's my RC discharging. There's the answers to my questions. So now you can go ahead and submit the PDF to your professor, and it will keep all the same formatting that you see on your document. So there's just a couple things I want to talk about here before I finish up. You'll notice when we did the screen capture, we have all these little dots in the background here. So if you go to Multisim, these are the little dots we're talking about. So if you go to View, you can actually come down here to Grid, and that'll turn off all the dots. So you might want to turn off those dots before you do your screen capture. So just a couple points about the simulation I want to mention. When you're looking at this particular circuit, if I close the switch, the capacitor should charge up to the total voltage. And you'll notice in this simulation, it doesn't. So sometimes adding a switch can stop your simulation from actually working. The other thing to note is, see down here where we have the time going? This is not actual real time. This is simulation time. So if we were to compare the simulated time to actual time, in my case I found out simulated time took twice as long as real time. So for instance, if I stop my simulation here at 20 seconds, in real time that was actually 40 seconds in my case. So just a few things to keep in mind when you're doing your simulations.